Hello, everybody. I'm back again with another video. I had noticed that people on my YouTube channel been interested in problems that are involving gears and pulleys. I have already one example related to uh, pulleys and belts. So I thought maybe I should show you an example of you know, gears and gear ratios. So this is a very simple example. I mean, the picture looks, the problem looks kind of overwhelming, but it's really simple once you know how to handle the gear ratio. Uh, Again, just in case if this is the first time you see my video, my name is Masood Olia, and I'm a faculty in the School of Engineering at Wentworth University. And I have a YouTube channel which consists of different topics, different playlists of dynamics, mechanics of materials, vibrations, and statics, and so on. Okay, so what are we trying to do here, guys, in this problem? So let's say we turn the motor on here, right? And the motor gives us an angular acceleration of 2 radians per second squared, and it's a constant. So basically the shaft of this motor, which is attached to gear A, is going to rotate with this angular acceleration. Now, what we want to determine is after 10 seconds, or at t equal 10 seconds, how much in millimeters this load W is going to be lifted up. So it's going to move up. So let me actually first tell you how can we calculate, what do we need to figure out that S, I'll call it S of W, the vertical motion of this load. And you guys know that, you see how this cable is going around this spool, E, whose radius is 50 millimeters, right? And of course, that spool is also a shaft which is attached to gear D. So in a way, if you look at it this way, in a simple way, this is the radius of that shaft or spool here, right? And let's say if I could figure out how much this guy rotates, you know that the arc length, see this arc length, represents actually this S, right? And you know from the simple geometry that simply is R times theta. And that would be what? R of this shaft or spool times how much this guy rotates. Of course, this theta sub must be in radians for this to work. So it has to be dimensionless. So, excuse me. So what is the theta of E? Well, theta of E is the same as theta of this gear D. So in a way, the S sub W is this radius of E, which you can see here in the picture is 50 millimeters, right? Times theta sub D, because theta E and theta D are equal. They are connected through a shaft. So the center of that shaft E is connected to, the shaft E is connected to the center of gear D. So in a way, if I could figure out in 10 seconds how much this gear D is going to rotate, then I can easily find how much this load is lifted. So how am I going to do that? So basically, this is where the gear ratios come in. Let me start by figuring out how much this guy will rotate, how many radians this guy will rotate in 10 seconds. And I was this shaft coming from the motor. So if you have a constant acceleration with basically two integration, alpha is the integral of omega. Omega is the integral of alpha. I have it wrong because remember, alpha is what? The derivative of omega, right? And then also, omega is what? The rate of change of angle theta. And therefore, theta is the integral of omega. Well, or you do have this CAN formula. For example, if you go through the integration twice, you end up getting this formula, which you should be familiar with. this equation. So starting from rest, all I have to do, and this, by the way, is theta of A, because that shaft is connected to gear A. So that would be 1/2 alpha of the motor, which is 2, right? And 10 seconds later, this becomes 100 radians. So shaft, which is connected to gear A, in 10 seconds is going to go through 100 radians, right? So now this is where the gear ratio comes in, guys. So gear ratio basically matching the S, which is the R theta between gear A and gear B. For example, if you want to find theta B, the ratio of theta B over theta A is simply the ratio of gear radio of gear A to gear B. See that? If you do cross multiplication, RA theta A is equal to RB theta B, which means they're going through the same S, okay, arc length. Also, notice that once you determine theta B and theta C are the same. You see, you could make a note here that theta C is the same as theta B, right? How much B and C are going is going to be the same in terms of the angular rotation. So now I'm going to do one more gear ratio between gear C and D. And so that is theta sub D. Remember, I eventually want to find theta sub D, right? That's what I want. So theta sub D over what? Theta sub C, I'm running out of space here, guys, is again the same ratio. It's the inverse ratio. It has to be RC over RD. So look, guys, from here, I can say theta sub D is RC over RD theta sub D. But remember, theta sub C and theta sub B are the same, so this becomes RC over RD, right? Replace theta C here by theta B. But what is theta B? Look, do the same thing, the same cross multiplication here. Look, theta B is what? RA over RB times theta A. So look what happens eventually. So here, RC over RD, right? Theta B is what? Right here. RA over RB theta A. Or you could do it step by step if you want. Doesn't really make any difference. So look, here's my final equation to getting how much D is going to rotate. So theta sub D is equal to this. RC over RD. And remember, all the radii are given for different gears. RA over RB, theta A. And I know what theta A is. I calculated theta A for you here, 100 radians. So let's go ahead and see what they are. I want the ratio of RC to RD. RC is 30 millimeters over 300 millimeters. By the way, this is not clearly to scale, guys, in terms of the picture. Then RA to RB. Again, you could see RA is 40 millimeters, RB 225. That doesn't look really good in the picture, at least. And then finally, theta A, which is 100 radians. So look, if you do the calculations, you get 1.78 radians. So basically, the motor is giving you 100 radians of rotation in 10 seconds, or at least the shaft of it. But actually, this we're doing through reduction. So basically, it's reduced by like, kind of like, looks like more than 50 times reduction. Okay, from 100 to, say, 1.78, more than 50. All right, and then you guys remember that at the beginning of this video, I said, well, look, S sub W is R of E. R of E was what? 50 millimeters, right? The radius of this spool here, that here, that's a 50 millimeters here, right? This guy, right? Times what? The 1.78 that I got. Look, the radians, I'll put the units here for you. So 50 millimeters times 1.78 That's nothing, 88.89 millimeters, almost 89 millimeters of movement up. So it's being lifted. So basically we had here reduction of motion. So actually the speed is going down, or as a result, theta started with theta of 100 radians, the theta has gone down. Okay, guys, thank you for watching and listening. And as always, if you like the video, please go ahead and like the video and leave any comment you have, and subscribe to my channel. I'll see you guys soon. Thank you.